In the sea of stars, planets, and galaxies lies a realm of particles, tiny fragments of matter that can travel across vast distances at unimaginable speeds. Some of these particles are harmless, passing through us every second without leaving a trace. But others are far more dangerous, carrying the potential to disrupt technology, alter planets, or even threaten life itself. From cosmic rays that bombard Earth from deep space to strange matter that could turn everything it touches into something entirely different. These tiny entities hold the power to shape the cosmos. What makes them so dangerous, and how close are we to understanding their full impact? Join me as we explore these questions along with their unsettling answers. Neutrinos, the ghost particles. Neutrinos are some of the most elusive particles in the universe. Unlike other particles that make up the familiar world around us, neutrinos pass through matter almost entirely undisturbed. Every second, trillions of neutrinos shoot through your body, but you don't feel them, and they don't leave a trace. Their ability to interact so weakly with matter has earned them the nickname ghost particles. But then why are they so dangerous? Neutrinos are produced in a wide range of processes, from nuclear reactions in stars to the radioactive decay of elements on Earth. One of the most significant sources of neutrinos is the Sun, releasing vast amounts of energy in the form of light and heat. These reactions also produce a constant stream of neutrinos that travel outward, escaping the Sun and spreading through the solar system. Neutrinos created in the Sun are known as solar neutrinos, and they are one of the primary types that reach Earth in large numbers. Despite their weak interactions with matter, neutrinos do have some interesting properties that make them important to study. These flavors can change as neutrinos travel through space, a phenomenon known as neutrino oscillation. The weak interaction between neutrinos and matter also means that detecting them is an incredibly difficult task. Since neutrinos can pass through entire planets' worth of material without slowing down, traditional methods of detection, which rely on particles interacting with a medium, are largely ineffective. Instead, scientists use highly sensitive detectors placed deep underground or beneath large bodies of water to increase the chance of capturing the very rare interactions between neutrinos and other particles, equipped with sensors to detect the faint flashes of light produced when a neutrino occasionally collides with an atom. Even though neutrinos rarely interact with matter, their presence is essential in some of the most energetic and violent processes in the universe. Supernova explosions, for example, produce an enormous burst of neutrinos as a dying star collapses under its own gravity. During a supernova, the core of the star implodes. The neutrinos emitted during a supernova carry away a significant portion of the star's energy, allowing the outer layers of the star to explode outward. Detecting neutrinos from a supernova provides valuable information about the explosion itself, as well as the conditions inside the star's core. In 1987, a supernova known as SN 1987A occurred in a neighboring galaxy called the Large Magellanic Cloud. It was the closest supernova observed in modern times, and it provided a rare opportunity for scientists to detect neutrinos from such an event. Because of their weak interaction with matter, neutrinos can escape the star long before the blast itself becomes visible to telescopes. In fact, they are the first messengers of a supernova, often arriving at Earth hours before the light from the explosion reaches us. This early detection gave astronomers a glimpse into the processes occurring deep within the collapsing star before the explosion became visible in telescopes. In addition to supernovae, neutrinos are also produced in other cosmic events, such as the collisions of black holes and neutron stars, and in gamma-ray bursts. These high-energy events produce neutrinos with even greater energy than those generated by the Sun or radioactive decay on Earth. Studying these high-energy neutrinos provides valuable insights into the most extreme environments in the universe. Neutrinos are one of the most abundant particles in the universe. For every cubic centimeter of space, there are roughly 330 relic neutrinos left over from the immediate aftermath of the Big Bang. And countless more neutrinos are produced every second in stars, supernovae, and other cosmic events. This abundance, combined with their ability to travel vast distances without being absorbed, makes neutrinos an essential tool for studying the universe. By detecting and studying neutrinos, scientists are uncovering new information about some of the most violent and energetic processes in existence, as well as the hidden workings of the cosmos. However, the very property that makes neutrinos so fascinating, their weak interaction with matter, also raises questions about their potential dangers. Since they pass through nearly everything without interacting, it's easy to assume that neutrinos are harmless. And for the most part, they are. But when neutrinos are produced in extremely high energy events, like those involving black holes or gamma-ray bursts, the particles can pack a much more powerful punch. High-energy neutrinos, while rare, have the potential to cause damage if they were to interact with matter in just the right way. The sheer number of neutrinos in the universe means that even a small fraction of interactions could have a significant impact. For example, high-energy neutrinos generated by a supernova or a black hole collision could potentially disrupt electronics or biological systems if they were intense enough. Supernova neutrinos, the lethal echo of stellar deaths. Supernovae are among the most violent and dramatic events in the universe. When a star reaches the end of its life, it can explode in a supernova, releasing an enormous amount of energy in a brief moment. These explosions not only send shockwaves and stellar debris across space, but they also unleash a flood of neutrinos. In fact, most of the energy released during a supernova doesn't come in the form of light or heat. It comes in the form of neutrinos. These particles shoot out in all directions, traveling vast distances and carrying with them the final deadly echo of the star's collapse. The neutrinos produced in a supernova are astonishing in both their number and energy. During the collapse of a massive star's core, neutrinos are generated as nuclear reactions run wild, and within seconds, the star ejects as many as 10 to the power of 58 neutrinos into space. These neutrinos travel at nearly the speed of light, unimpeded by the stellar material that would block other forms of radiation. For life on Earth, the threat posed by supernova neutrinos would depend largely on how close the explosion occurs. If a supernova happens far enough away, at distances greater than 50 light-years, its neutrino burst would likely pass through the planet with little consequence. However, if a supernova were to occur closer to Earth, within a few dozen light-years, the neutrino shower could become more dangerous. Given the vast number of neutrinos that would bombard the planet, even their normally low interaction rate could be enough to damage living tissues. The neutrino burst could also affect ground-based technology. Nuclear reactors, for instance, could be susceptible to interference from the high-energy particles. The flood of neutrinos might increase the background radiation levels within reactors, potentially causing operational difficulties or safety concerns. Similarly, particle accelerators and other scientific instruments that rely on precise measurements of subatomic particles could be thrown off by the sudden influx of neutrinos, complicating experiments or forcing temporary shutdowns. Perhaps the greatest concern, however, lies with the long-term effects of a nearby supernova's neutrino burst on the planet's atmosphere. High-energy neutrinos could initiate chemical reactions in the upper atmosphere, leading to the breakdown of important molecules such as ozone. The destruction of the ozone layer, which protects life on Earth from harmful ultraviolet radiation, could have disastrous consequences. Without this protective shield, the planet would be exposed to far greater levels of UV radiation from the sun, increasing the risk of skin cancer, cataracts, and other health problems in humans and animals. The loss of ozone would also disrupt ecosystems. Thankfully, the risk of a supernova occurring close enough to Earth to cause significant harm remains relatively low. The nearest known supernova candidates, such as the red supergiant star Betelgeuse in the constellation Orion, are still far enough away that their explosions are unlikely to pose a serious threat. However, the unpredictability of supernovae means that astronomers continue to monitor potential candidates closely, both to understand the physics of these massive explosions and to assess any potential risks to life on Earth. Antimatter in the wild. Rare, elusive, and destructive. Antimatter counts as one of the most dangerous substances in the universe. It is the mirror image of regular matter, with particles that have the same mass as their ordinary counterparts, but opposite charges. When antimatter meets regular matter, they annihilate each other in a burst of energy, releasing incredible amounts of power. This process is efficient and violent, making antimatter one of the most destructive forces in the universe. While antimatter is rare in nature, it does exist, and it can be found in some of the most extreme environments in space. One of the most common sources of naturally occurring antimatter comes from cosmic rays. When cosmic rays collide with atoms in Earth's atmosphere, or with other particles in the interstellar medium of space, they sometimes produce antimatter. This antimatter typically takes the form of positrons, the antimatter equivalent of electrons, which have a positive charge instead of a negative one. In space, antimatter is often fleeting, lasting only a brief moment before it encounters regular matter and annihilates in a flash of energy. But there are places where antimatter seems to accumulate. For instance, near pulsars, rapidly spinning neutron stars with intense magnetic fields, scientists have observed evidence of antimatter. These pulsars create powerful magnetic fields that accelerate particles to near-light speeds. In this chaotic environment, collisions between high-energy particles can produce antimatter, which is then trapped by the pulsar's magnetic field. This makes pulsars one of the few places where antimatter is naturally concentrated. Beyond pulsars, there are regions of the Milky Way where antimatter can be detected. Observations using gamma-ray telescopes have revealed that the core of our galaxy produces a steady stream of gamma rays, a sign of antimatter annihilation. Scientists are still unsure about the exact source of this antimatter, but theories suggest it could come from a number of processes, including black holes, dark matter interactions, or the remains of past supernova. The energy produced from matter-antimatter annihilation is far greater than that from nuclear reactions like fission or fusion. In fact, even a tiny amount of antimatter could release as much energy as a large conventional bomb. This destructive potential has made antimatter a subject of intense study, both for its role in cosmic phenomena and for its possible use in energy production or weapons. The rarity of antimatter in nature is one of the great mysteries of physics. According to current theories, the Big Bang should have created equal amounts of matter and antimatter. Yet, the universe as we see it today is almost entirely made of matter, with antimatter being incredibly rare. This imbalance has puzzled scientists for decades. If matter and antimatter were created in equal amounts, why did matter win out? What happened to the antimatter? These questions remain unanswered, and understanding the nature of antimatter could unlock new insights into the origins of the universe. Because matter-antimatter annihilation is so efficient, even a small amount of antimatter could provide a tremendous amount of power. Some scientists have proposed using antimatter as fuel for spacecraft, allowing them to travel at much higher speeds than would be possible with conventional rocket fuel. However, creating and storing antimatter is extremely difficult. Currently, antimatter can only be produced in minute quantities in particle accelerators, and it requires vast amounts of energy to create even a tiny fraction of a gram. Storing antimatter is another challenge, as it must be kept completely isolated from regular matter to prevent it from annihilating. Cosmic rays, messengers from beyond the solar system. Cosmic rays are high-energy particles that come from places far beyond our solar system. These tiny, invisible travelers move through space at nearly the speed of light. These rays aren't rays in the way we might think of light or radiation. They come from outside the protective bubble of our solar system, known as the heliosphere. This means that cosmic rays have traveled vast distances, possibly for millions of years before reaching Earth. Their journey may have begun in far-off galaxies or during violent events like supernovae, where stars explode at the end of their lives. When we think of space, it often seems like a vast, empty void, but cosmic rays show that this emptiness is full of activity. As they travel, cosmic rays encounter magnetic fields, gas clouds, and other particles. These interactions sometimes change their direction or energy, but they still manage to travel incredible distances. Once they enter the solar system, they face the sun's magnetic field, which can deflect or slow them down. However, some of the highest energy cosmic rays push through these defenses, continuing their journey towards Earth. The origins of cosmic rays are still somewhat of a mystery. While scientists have a good understanding of where some of them come from, like the sun, the origins of the most energetic cosmic rays remain unclear. Many believe they are born in violent cosmic events, such as supernovae explosions. When a star explodes, it releases a vast amount of energy, and some of this energy is transferred to nearby particles, flinging them out into space as cosmic rays. Others might come from even more extreme environments, like black holes or the centers of distant galaxies. These locations are known to have powerful magnetic fields that could accelerate particles to the incredible speeds we see in cosmic rays. Cosmic rays have traveled across unimaginable distances, dodging obstacles and interacting with the universe's structures. Their journey is shaped by magnetic fields, supernova remnants, and even the occasional collision with other particles. But they aren't exactly silent, harmless travelers. When these high-energy particles collide with matter, they can cause significant damage. For spacecraft and satellites, which spend years in space, cosmic rays pose a constant risk. These particles can penetrate metal and other materials, disrupting the delicate electronics that power our technology. Over time, the effects of these collisions accumulate, causing equipment to malfunction, or in some cases, completely fail. When a cosmic ray strikes a piece of electronic equipment, it can cause a phenomenon known as a bit flip, where the cosmic ray alters the state of a single bit of data in the computer's memory. This may sound trivial, but in some cases these errors can cause malfunctions or failures in critical systems. Satellites, spacecraft, and even Earth-based technologies like power grids and communication networks could potentially be affected by bursts of cosmic rays from high-energy sources. One of the biggest concerns is the potential harm cosmic rays can cause to astronauts. Space is a harsh environment, and while the Earth's magnetic field protects us from most cosmic rays, astronauts don't have that same shield when they venture beyond low Earth orbit. Even the thick walls of spacecraft provide only limited protection. As cosmic rays pass through a person's body, they can ionize the atoms inside. This ionization can damage cells and DNA, increasing the risk of cancer and other long-term health problems. For long-duration missions to places like Mars, cosmic rays become a serious challenge. Exposure over extended periods could lead to significant health issues, which is why scientists are working to develop better protective measures for astronauts on these missions. They also have an impact on our planet, despite the Earth's atmosphere acting as a powerful shield. Most cosmic rays are blocked before they can reach the surface, but some of them still manage to penetrate the atmosphere. When cosmic rays collide with molecules in the atmosphere, they create showers of secondary particles, which can be detected by special instruments on the surface, providing valuable data on cosmic rays. Studying cosmic rays has proven to be difficult. Because they are so energetic, it's hard to capture and observe them directly. However, scientists have developed clever methods to study these elusive particles. One of the most famous cosmic ray detectors is the Alpha Magnetic Spectrometer, which is mounted on the International Space Station. This instrument helps scientists learn more about the particles that make up cosmic rays and the energy they carry. Some scientists believe that cosmic rays could influence star formation by interacting with the clouds of gas that eventually collapse to form stars. The idea is that cosmic rays may inject energy into these gas clouds, either helping them collapse or, in some cases, preventing them from doing so. This influence, if proven true, could have major implications for how we understand the life cycles of galaxies. Air showers. What happens when cosmic rays hit Earth's atmosphere? When cosmic rays reach Earth, most of them don't make it to the ground in their original form. Instead, they collide with atoms in the atmosphere, triggering a cascade of secondary particles. This process is known as an air shower. These showers are the result of a high-energy cosmic ray, often a proton. The collision creates new particles that continue to travel downward, spreading out as they move. What starts as a single, fast-moving particle from space quickly becomes a vast shower of many particles. Some of the particles created during these collisions are short-lived, existing only for a fraction of a second before decaying into other particles. Others travel all the way to the surface, so cosmic rays, even though they don't often reach the surface in their original form, still leave their mark on the planet. Air showers aren't visible to the naked eye, but scientists have developed special detectors that can capture the particles as they rain down. When the high-energy particles in an air shower strike the Earth, they can produce tiny flashes of light, which can be picked up by sensitive cameras. Large arrays of detectors are spread out across areas of land, such as the Pierre Auger Observatory in Argentina, to monitor these showers. By studying the patterns of these air showers, researchers can learn more about the properties of the original cosmic ray that caused them, such as its energy and the direction it came from. While cosmic rays themselves are dangerous, air showers also pose potential risks. The secondary particles created in these showers contribute to radiation exposure on Earth, though most of the time this exposure is minimal. Earth's atmosphere does a good job of absorbing much of the radiation before it reaches the surface, but the higher up you go, the less protection there is. This is why people who spend a lot of time flying at high altitudes, like airline pilots and crew members, are exposed to more cosmic radiation than those on the ground. Air showers also have an impact on technology, particularly for systems that operate in the upper atmosphere or in space. Satellites, for example, are subject to the constant bombardment of secondary particles from air showers. Over time, this exposure can cause electronic malfunctions or even permanent damage. It's a serious concern for space agencies and companies that rely on satellites for communication, navigation, and observation. At high altitudes, where the air is thinner and there is less atmosphere to absorb cosmic radiation, air showers are a more frequent occurrence. This means that people living or working in these environments are exposed to slightly higher levels of cosmic radiation. In the past, high-altitude balloon experiments have been used to study these effects. By sending detectors up into the atmosphere, scientists have been able to measure the levels of radiation and the characteristics of air showers at different altitudes. Cosmic rays and air showers provide important information about the universe beyond our planet. These high-energy particles carry clues about the most violent and energetic events in space, from supernovae to black holes. By studying the air showers they produce, scientists can piece together a picture of the cosmic ray's journey from its origin to Earth. Each air shower is like a fingerprint, providing unique information about the cosmic ray that caused it. A single cosmic ray can produce billions of secondary particles, each interacting with the atmosphere in different ways. These interactions are influenced by factors such as the energy of the cosmic ray and the density of the atmosphere. Because of this, predicting exactly how an air shower will unfold is difficult. Scientists use computer models and simulations to better understand the process and make predictions about what kinds of particles will be produced in a given collision. Cosmic rays and air showers also provide insights into fundamental physics. The collisions that happen in the atmosphere are similar to those created in particle accelerators on Earth, like the Large Hadron Collider. When a cosmic ray strikes an atom in the atmosphere, the energy released is so great that it can break the atom apart, creating a shower of subatomic particles. By studying these particle showers, scientists can learn more about the forces and interactions that govern matter at the smallest scales. Some researchers hope that cosmic rays and air showers could provide clues to new physics beyond the Standard Model, the framework that currently explains the behavior of particles and forces. The high-energy punch of ultra-high-energy cosmic rays, UECAs. Cosmic rays come in many forms, But there is a specific class that stands out due to its sheer power: ultra-high energy cosmic rays, or UHECRs. These are particles with energies far beyond those of typical cosmic rays, reaching levels that human technology has yet to replicate. While cosmic rays themselves are already energetic, with particles traveling close to the speed of light, UECRs take this to another level. They carry such enormous energy that they challenge our understanding of how such particles could even be accelerated to these speeds in the first place. Regular cosmic rays are mostly made up of protons and atomic nuclei. They can have energies ranging from a few billion electron volts to several trillion electron volts, which is already extremely powerful. But UHECRs, the most energetic class, are different. Their energy levels surpass anything we can achieve in particle accelerators like the Large Hadron Collider. These particles can have energies greater than 10 to the power of 18 electron volts, and in some cases, they can reach beyond 10 to the power of 20 electron volts. To put this in perspective, a single UHECR striking the Earth carries as much energy as a fast-pitched baseball or a car moving at moderate speeds. Yet, it's all packed into a single subatomic particle, a mind-boggling concept considering their size. Scientists have been able to trace some cosmic rays back to known sources, like supernovae or solar flares. But the origin of UHECRs is still largely unknown. Their extreme energies suggest they come from very violent and energetic events in the universe, such as the environment surrounding supermassive black holes or the remnants of ancient gamma-ray bursts. These are some of the most powerful phenomena in the universe, capable of releasing enormous amounts of energy in short bursts. However, the mechanisms that accelerate particles to the energies seen in UHECRs remain a mystery. No known natural process seems fully capable of giving these particles their incredible energy. Traveling at close to the speed of light, these particles move through space, encountering magnetic fields and other obstacles along the way. Because of their high energies, they are less affected by these magnetic fields than regular cosmic rays. This means they travel in almost straight lines, making it easier to trace their path back to their source, at least in theory. But even with this advantage, pinpointing where UHECRs come from has proven to be incredibly difficult. Part of the challenge is that these particles are so rare. While cosmic rays hit the Earth's atmosphere constantly, UHECRs are much more infrequent, with only a few striking Earth per square kilometer each year. When they do collide with the Earth's atmosphere, they produce massive air showers, similar to regular cosmic rays, but on a much larger scale. The secondary particles created in these air showers spread out over a wide area, and detecting them requires large arrays of sensors covering vast regions of land. UHECRs can be very dangerous because of the extreme energy they carry. When these particles collide with atoms in the atmosphere, they release vast amounts of energy in the form of secondary particles. These collisions can cause significant damage to anything in their path, especially in space where there's little protection. UHECRs offer a unique window into some of the most extreme environments in the universe. They could provide clues about the most energetic and violent processes in the universe, such as the formation of black holes, the merging of neutron stars, or the rapid rotation of pulsars. These are events that cannot be easily studied by traditional means, but UHECRs, as messengers from these distant locations, carry valuable information about these processes. However, their rarity makes them difficult to study. Detecting even a few of these particles requires years of careful observation, and the vast energy they carry makes it hard to predict their behavior. There is also an intriguing question about whether UHECRs could originate from exotic sources, such as the decay of hypothetical particles left over from the Big Bang. Some theories suggest that UHECRs could be linked to particles that we have yet to detect or understand, potentially offering insights into the earliest moments of the universe. Gamma-ray bursts, the universe's most powerful explosions. Gamma-ray bursts, or GRBs, are among the most violent and powerful events in the universe. These intense flashes of gamma radiation can release more energy in a matter of seconds than our sun will emit over its entire lifetime, which spans billions of years. The sheer magnitude of energy contained in a GRB makes them some of the most energetic and dangerous phenomena in existence. Even though they happen far away in distant galaxies, the potential danger of these bursts extends across vast stretches of space. GRBs come in two main types: long-duration and short-duration bursts. Long-duration bursts, which last anywhere from 2 seconds to several minutes, are thought to be caused by the collapse of massive stars at the end of their life cycles. When a star much more massive than the Sun runs out of fuel, it can collapse under its own gravity, forming a black hole. In the process, the outer layers of the star are blown away in a supernova explosion, and if conditions are right, the core can emit a focused jet of gamma radiation into space. This is what we observe as a gamma-ray burst. Short-duration bursts, on the other hand, are much quicker, lasting less than 2 seconds, and are believed to come from the collision and merger of two neutron stars, or a neutron star and a black hole. These bursts are difficult to observe directly because they are so brief and happen unexpectedly, often in distant parts of the universe. However, modern telescopes and satellites are equipped to detect the high-energy radiation emitted by GRBs. The bursts are detected as sudden spikes in gamma radiation, often accompanied by an afterglow in other parts of the electromagnetic spectrum, such as X-rays or visible light. This afterglow can last for hours, days, or even weeks, providing more time for scientists to study the event and its aftermath. The danger posed by gamma-ray bursts comes from the immense energy they release, which is concentrated into a narrow beam. If one of these bursts were to occur relatively close to Earth and was pointed in our direction, the effects could be catastrophic. The radiation from a GRB could strip away the planet's ozone layer, leaving life on Earth exposed to harmful ultraviolet rays from the Sun. This exposure could lead to mass extinctions, similar to what some scientists believe might have happened in our planet's past. Fortunately, gamma-ray bursts are rare, and the likelihood of one happening close enough to Earth to cause direct harm is extremely low. Most GRBs occur in distant galaxies, hundreds of millions or even billions of light-years away from us. Even though they release vast amounts of energy, the distance between these events and Earth is usually so great that their effects are diluted by the time they reach our planet. However, astronomers keep a close eye on GRBs, as they provide a window into some of the most extreme processes in the universe. The energy released by a GRB comes in the form of gamma radiation, the most energetic type of electromagnetic radiation. Gamma rays have much higher energy than visible light or even X-rays, and they can penetrate through most materials. On Earth, gamma rays are produced by radioactive decay, nuclear reactions, and certain high-energy processes in space. However, the gamma rays from a GRB are on an entirely different scale. A single burst can emit as much gamma radiation as the rest of the universe combined in the same amount of time. This incredible release of energy is what makes GRBs so powerful and potentially dangerous. Short-duration GRBs, which are caused by the merger of neutron stars or black holes, also provide valuable insights into the behavior of these dense objects. Neutron stars are the remnants of massive stars that have exploded in supernovae, leaving behind incredibly dense cores. When two neutron stars collide, the energy released is enough to create a gamma-ray burst, along with gravitational waves, ripples in space-time that can be detected by instruments on Earth. The detection of both gamma rays and gravitational waves from a single event provides scientists with a unique opportunity to study the universe in multiple ways, helping to confirm theories about the nature of these collisions. The discovery of gamma-ray bursts was initially accidental. In the 1960s, military satellites designed to detect nuclear explosions on Earth picked up unexpected bursts of gamma radiation from space. At first, these signals were a mystery, but over time scientists began to realize that they were coming from distant cosmic sources. This marked the beginning of the study of GRBs, which has since become a major field of research in astrophysics. Because they happen so quickly and without warning, it's difficult to observe them in real time. However, advances in technology have made it possible to detect GRBs almost as soon as they occur. Satellites like NASA's Swift and Fermi observatories are designed to monitor the sky for bursts of gamma radiation. When a burst is detected, these satellites quickly alert ground-based telescopes, allowing scientists to observe the afterglow and gather as much information as possible before it fades. Because GRBs are so bright and can be seen from billions of light-years away, they provide a way to observe parts of the universe that would otherwise be too distant or faint to study. The light from a GRB can also pass through clouds of gas and dust, providing information about the composition and structure of these regions. By analyzing the light from a gamma-ray burst, scientists can learn about the environment in which the burst occurred, as well as the galaxies and other structures that the light passes through on its way to Earth. The role of magnetic fields in steering cosmic rays. Cosmic rays travel through the universe at incredible speeds, carrying energy and radiation from distant parts of space. However, their paths are not always straightforward. One of the main factors that influences the trajectory of cosmic rays is the presence of magnetic fields. These fields are scattered throughout the cosmos, generated by planets, stars, and galaxies. Magnetic fields can bend, redirect, or even trap cosmic rays, changing their course as they move through space. The Earth's magnetic field is one of the most important shields protecting life on our planet from harmful cosmic rays. This magnetic field, known as the magnetosphere, surrounds the Earth like a giant bubble, extending far into space. As cosmic rays approach the Earth, they encounter this magnetic field, which deflects many of the particles away from the planet. The way magnetic fields interact with cosmic rays depends on the energy and charge of the particles. Lower energy cosmic rays, for example, are more easily deflected by magnetic fields, while UHERs are less affected. The deflection of cosmic rays by magnetic fields is governed by a principle called the Lorentz force. This force acts on charged particles as they move through a magnetic field, causing them to change direction. Cosmic rays are often made up of charged particles, like protons or atomic nuclei, which makes them susceptible to this force. As a cosmic ray passes through a magnetic field, it doesn't travel in a straight line. Instead, its path is bent, sometimes dramatically, depending on the strength and orientation of the magnetic field. This bending can prevent many cosmic rays from directly hitting Earth, reducing the amount of radiation that reaches the surface. Planets with strong magnetic fields, like Earth and Jupiter, are better protected from cosmic rays, while planets without magnetic fields, like Mars, are more exposed. Mars, for example, has only a weak magnetic field, which provides little protection against cosmic rays. As a result, the surface of Mars is bombarded with higher levels of radiation than Earth. Any mission to Mars would need to account for the increased radiation exposure astronauts would face on the planet's surface. Similarly, the Sun has its own powerful magnetic field, which extends far beyond the orbit of Earth. This field, known as the heliosphere, forms a protective bubble around the entire solar system. As cosmic rays travel through the galaxy, they enter the heliosphere and are slowed or deflected by the Sun's magnetic influence. The heliosphere helps shield the inner planets, including Earth, from a significant portion of galactic cosmic rays. However, this protection is not absolute. Some cosmic rays, particularly the higher energy ones, can still penetrate the heliosphere and make their way toward Earth. The strength of the heliosphere's protection varies over time. The Sun goes through an 11-year cycle of solar activity, during which the strength and structure of its magnetic field changes. During periods of high solar activity known as solar maximum, the Sun's magnetic field is stronger and more chaotic. This can lead to increased deflection of cosmic rays, meaning fewer rays reach the inner solar system. Conversely, during solar minimum, when the Sun's magnetic field is weaker, more cosmic rays are able to pass through the heliosphere. This fluctuation in cosmic ray exposure can affect both space exploration and life on Earth. Astronauts traveling through space during solar minimum are exposed to higher levels of cosmic radiation because the Sun's magnetic shield is weaker. Magnetic fields also exist on a much larger scale throughout the galaxy. The Milky Way, like many galaxies, has its own magnetic field that stretches across unimaginable distances. This galactic magnetic field can influence the paths of cosmic rays as they travel from distant parts of the universe. As cosmic rays move through the galaxy, they are bent and twisted by these magnetic fields, making it difficult to trace their origins. By the time a cosmic ray reaches Earth, its path has often been altered so many times that it is nearly impossible to determine where it originally came from. This makes studying the sources of cosmic rays particularly challenging for scientists. Certain celestial objects like neutron stars and black holes have disproportionately strong magnetic fields, which can trap and accelerate cosmic rays to even higher energies. The intense magnetic fields around black holes, for instance, can produce jets of high-energy particles that shoot out into space at nearly the speed of light. These jets are thought to be a source of some of the highest energy cosmic rays in the universe. Magnetic fields can also influence cosmic rays in more subtle ways. When cosmic rays encounter magnetic fields, they can become trapped, spiraling around magnetic field lines and traveling along them. This phenomenon can be observed in the Earth's magnetosphere, where charged particles from the solar wind are captured by the planet's magnetic field and funneled toward the poles. When these particles collide with atoms in the Earth's atmosphere, they produce the glowing lights of the auroras, also known as the northern and southern lights. Antiprotons, the rare visitors in cosmic rays. Antiprotons, a specific kind of antimatter particle, are rare but significant travelers in the universe. Like positrons, which are the antimatter counterparts of electrons, antiprotons are the mirror images of protons. They have the same mass as protons but carry a negative charge. Antiprotons are not easily created. They form under extreme conditions, such as in high-energy collisions between particles. These collisions can happen in places like supernovae, the explosive deaths of massive stars, or in regions surrounding black holes where matter is being torn apart. When cosmic rays travel through space, they often collide with interstellar gas or other particles, producing antiprotons as a result of these violent interactions. Despite their rarity, antiprotons do reach Earth. Just like other cosmic rays, they traverse vast distances through the galaxy before encountering our planet. As they approach Earth, they must pass through the magnetic fields that surround our planet. These fields, part of Earth's natural protective shield, can alter the paths of charged particles like antiprotons. In some cases, this magnetic deflection prevents these particles from ever reaching the ground, while in other instances they are funneled into the atmosphere, where they interact with atoms, creating secondary particles. When antiprotons do reach Earth's atmosphere, they face a harsh environment. Almost immediately, they encounter regular matter, triggering annihilation events. During these events, the antiproton and a proton from the surrounding matter annihilate each other, releasing energy in the form of gamma rays. Since the mass of a proton is over 1,000 times greater than the mass of an electron, the energy released from a proton-antiproton annihilation event is also significantly greater than that released by electron-positron annihilation. While the number of antiprotons reaching Earth is small, if a concentrated burst of antiprotons were to hit the planet, it could cause localized disruptions. The gamma rays produced in these annihilations could affect communication systems, satellites, and even electrical grids, although the risk to humans would likely be limited due to the protective nature of Earth's atmosphere. Most of the time, antiprotons that do reach Earth are few and far between, dispersed among the many other particles that make up cosmic rays. However, studying these particles is still important, as it helps scientists understand the extreme conditions in which they are created and how they behave in space. The origin of antiprotons in cosmic rays remains a subject of ongoing research. While it is generally agreed that many antiprotons are produced through the interactions of cosmic rays with interstellar matter, there is also speculation that some could be produced by more exotic processes. One possibility is that dark matter, the mysterious and invisible substance thought to make up a large portion of the universe, could produce antiprotons when it interacts with itself or with regular matter. Antiprotons also provide valuable information about the composition of cosmic rays. By comparing the number of antiprotons to protons in cosmic rays, researchers can learn more about the mechanisms that produce these particles and the environments they come from. For instance, if an unusually high number of antiprotons were detected, it could indicate a nearby source of antimatter, such as a pulsar or a region of space where dark matter is abundant. Strange matter, a new state of matter or a galactic catastrophe. While an electron is a fundamental particle, protons and neutrons are composites that are themselves a combination of smaller particles called quarks. A proton, for example, is made up of 2 up quarks and 1 down quark. There are 6 different types of quarks in the universe, including one called a strange quark. This type of subatomic particle that does not normally exist in stable forms on Earth. Strange matter, a form of quark matter, represents one of the most intriguing and potentially dangerous concepts in astrophysics. Unlike the protons and neutrons that make up the matter we are familiar with, strange matter is theorized to consist of up, down, and strange quarks. This exotic state of matter might exist deep within neutron stars, where immense gravitational forces compress matter into extreme densities. What makes strange matter truly dangerous is the hypothetical possibility that it could transform regular matter into more strange matter upon contact, a process that could lead to catastrophic outcomes on a cosmic scale. To understand the potential threat posed by strange matter, it's essential to look at its theoretical origins. Neutron stars, which form after the collapse of massive stars, are incredibly dense remnants composed mostly of neutrons. These stars are so dense that a single teaspoon of neutron star material would weigh about as much as a mountain on Earth. Under the extreme pressure at the core of these stars, it's possible that quarks break free from their bonds, forming a quark-gluon plasma. In this state, strange quarks could emerge, creating strange matter. The theory suggests that strange matter, if it exists, could be more stable than regular atomic matter. This stability is what makes it so dangerous. In a stable state, strange matter would have the potential to convert other forms of matter into strange matter as well. If a small chunk of strange matter, sometimes called a strangelet, came into contact with regular matter, it could initiate a chain reaction. The basic idea behind strangelets is that they could act like seeds of destruction. Their stability as a form of quark matter could make them dangerous in any environment filled with regular matter. If a strangelet were to interact with atoms composed of protons and neutrons, it could potentially trigger a reaction that turns those atoms into strange matter as well. This process, theoretically, could spread like a chain reaction, consuming more and more regular matter, converting it into strange matter, and continuing the destructive process, potentially spreading across an entire planet or beyond. This is what some researchers refer to as catalytic destruction, where one strangelet could convert a large amount of regular matter, leading to catastrophic outcomes on a planetary or even cosmic scale. If a strangelet were to escape from a neutron star and drift through space, it could, in theory, encounter a planet or a star. The strange matter would begin converting the regular matter it touches, expanding its reach as it consumes more material. The catastrophic scenario imagined by some scientists is that if strange matter were to reach Earth, it could trigger a chain reaction that would turn the entire planet into a mass of strange matter, obliterating all life and transforming the planet into a dense, lifeless object resembling a neutron star. While this scenario might sound otherworldly, it is based on real theoretical physics. However, it's important to note that, to date, there is no direct evidence that strange matter exists or that such a chain reaction could occur. Most of what scientists know about strange matter comes from complex models and simulations that explore what might happen under the extreme conditions found inside neutron stars. Still, the possibility is enough to warrant serious consideration. One of the reasons strange matter is so dangerous is its incredible density. In a sense, strange matter could be thought of as the densest form of matter that could exist outside of a black hole. Its gravitational pull would be immense, and the energy released during its interactions with regular matter would be enormous. If even a small amount of strange matter were to strike Earth, the resulting conversion process could release vast amounts of energy, potentially triggering massive explosions and catastrophic events on a global scale. Astrophysicists have speculated that strange matter could play a role in the violent collisions of neutron stars. When neutron stars merge, the extreme conditions at the point of collision could potentially create strange matter or release strangelets into space. These strangelets could then travel through the galaxy, presenting a potential hazard to any celestial bodies they might encounter. Some have even suggested that unexplained signals known as fast radio bursts, FRBs, could be the result of strange matter interactions during neutron star collisions, though this remains speculative. Conditions during the first few moments after the Big Bang were likely similar to those found inside neutron stars, with quarks and gluons existing in a plasma state before cooling and forming the protons and neutrons that make up ordinary matter. Strange matter, if it existed in the early universe, could have played a role in the formation of galaxies and other large-scale structures. One of the biggest concerns regarding strangelets is their potential formation during high-energy particle collisions. Experiments at particle accelerators, such as those conducted at CERN's Large Hadron Collider, create conditions that briefly resemble the extreme environments of the early universe or the interiors of neutron stars. Under these intense conditions, quarks can be liberated from protons and neutrons, forming a quark-gluon plasma. This plasma state, where quarks and gluons move freely, is where strange quarks could potentially combine with other quarks to form strangelets. Scientists carefully monitor these experiments, as the possibility of strangelet formation has been a matter of debate. While the chances are believed to be extremely low, the hypothetical risk is real enough to warrant caution. The concern is that if even a single strangelet were produced in a particle accelerator experiment, it could theoretically start a chain reaction. This could potentially cause a catastrophic event, as the strangelet could start converting ordinary matter into strange matter. However, most researchers agree that the conditions required to create stable strangelets are so extreme that it is unlikely they would be produced in a laboratory on Earth. Some models suggest that strangelets would decay quickly, making them less of a threat. Others, however, propose that strangelets could be incredibly stable, especially if they form in large enough quantities or under the right conditions. If stable strangelets were to exist and come into contact with Earth, the consequences would be disastrous. The idea of strangelets converting our planet into a strange matter object, similar to a neutron star, remains a disturbing possibility in the realm of theoretical physics. While strange matter could be extremely dangerous, it might also provide insights into the fundamental nature of the universe. If strange matter does exist, it could offer clues about the behavior of quarks and the forces that govern their interactions. Studying strange matter, either through indirect observations of neutron stars or through experiments that attempt to recreate similar conditions, could help physicists learn more about the strong nuclear force, one of the four fundamental forces of nature that holds atomic nuclei together. Tachyons, the impossible particles that could rewrite physics. A tachyon is a hypothetical particle that has sparked a great deal of interest in both science fiction and theoretical physics. Tachyons first emerged as a theoretical concept in the 1960s, a time when physicists were exploring the strange implications of quantum theory and relativity. According to Einstein's theory of relativity, nothing with mass can travel at or faster than the speed of light. The energy required to accelerate an object to that speed would become infinite. However, tachyons are a loophole in this understanding. Instead of starting at rest, and accelerating to light speed, tachyons are thought to exist naturally at speeds faster than light. In fact, they cannot slow down to light speed, just as regular particles cannot speed up to exceed it. The idea that such particles might exist opens up a new realm of possibilities, ones that could pose strange and unforeseen consequences for our understanding of physics, and perhaps even for the structure of the universe itself. If they exist, tachyons would have bizarre properties that make them fundamentally different from all other known particles. One of the strangest characteristics is that they would have an imaginary mass, a concept that doesn't align with our everyday understanding of reality. An imaginary mass would mean that the more energy a tachyon loses, the faster it moves, the exact opposite of how particles we know behave. The theoretical existence of tachyons was first proposed in the context of quantum field theory, where certain equations allow for particles with negative mass squared, a mathematical result that leads to faster-than-light motion. While this idea is intriguing, it has yet to be proven or observed. There is no experimental evidence to suggest that tachyons exist, but the concept remains a fascinating possibility, especially in the realm of theoretical physics, where exploring the boundaries of the known universe often involves examining things that might initially seem impossible. If tachyons were real, their existence could create serious issues for the concept of causality. Causality is a fundamental principle of the universe, stating that cause precedes effect. However, tachyons, with their faster-than-light speed, could theoretically allow for violations of causality. In some scenarios, events could occur out of order, with an effect being observed before its cause. For example, a signal sent using a tachyon could arrive at its destination before it was even transmitted. This leads to paradoxes, where the natural flow of time and the sequence of events would no longer make sense, potentially allowing for backward time travel or communication across time. These paradoxes have led many physicists to dismiss tachyons as purely speculative, as their existence would require a fundamental rewriting of how we understand time and space. However, some researchers argue that tachyons could exist in a way that doesn't violate causality, but would instead operate within their own unique set of physical laws that we have yet to fully understand. In this view, tachyons might interact with the universe in ways that are so foreign to our current models that they have gone undetected because our instruments and theories are not yet advanced enough to observe them. Since these particles would be constantly moving faster than light, they could potentially disrupt the structure of space-time, creating ripples or disturbances that could affect other particles and fields. This could have profound consequences on particle interactions, gravity, and even the expansion of the universe. Some theories suggest that tachyons could even play a role in the early moments of the Big Bang, contributing to the rapid inflation of the universe in its first fractions of a second. One particularly troubling possibility is that faster-than-light particles could interact with black holes in unexpected ways. Black holes already represent one of the most extreme environments in the universe, where the laws of physics as we know them break down. The singularity at the center of a black hole is a point where gravity becomes infinite and space-time is stretched to its limits. Tachyons, by moving faster than light, could potentially bypass the event horizon of a black hole, entering regions of space-time that are otherwise inaccessible. If this were the case, the effects could be profound. Tachyons might carry information from inside the black hole to the outside, violating the cosmic no-hair theorem, which states that black holes can only be described by their mass, charge, and spin. This could also undermine the principle of black hole entropy, which suggests that information entering a black hole is lost forever. If tachyons could escape from black holes, they could destabilize these dense objects and potentially alter the gravitational balance in their vicinity. There is also the question of how tachyons might interact with regular matter. As of now, no direct evidence of tachyons has been found, but if they were ever detected, one of the first concerns would be whether they could affect ordinary particles. Unlike cosmic rays, which have mass and can cause damage when they strike Earth's atmosphere, Tachyons, in theory, would behave very differently. Because they move faster than light, their interactions with regular matter might be brief and difficult to detect. However, if they do interact with other particles, they could transfer energy in ways we do not yet understand, potentially causing high-energy reactions. While this remains speculative, it's possible that tachyons could trigger particle cascades or other exotic phenomena that could have dangerous consequences on a larger scale. One potential danger of faster-than-light particles is the possibility of a tachyonic field, a field of energy made up of tachyons. If such a field were to exist, it could influence the behavior of particles across vast distances. Some theories propose that tachyonic fields could lead to spontaneous symmetry breaking, a process in which the fundamental forces of nature behave differently depending on the conditions. This is the same kind of process that is believed to have occurred during the early moments of the universe, leading to the separation of the forces we know today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. A tachyonic field might cause similar effects in localized regions of the universe, potentially altering the behavior of matter and energy in unpredictable ways. One of the key principles of quantum mechanics is that particles exist in superpositions of states until they are observed. If tachyons can move faster than light, they might interact with particles in these superpositions, collapsing their wave functions before the particles are measured. This would effectively break the principle of quantum uncertainty, which states that certain properties of particles, such as their position and momentum, cannot be precisely known at the same time. The violation of this principle would have profound implications for fields ranging from quantum computing to the study of subatomic particles. In particle physics, there is ongoing research into phenomena that might hint at the presence of tachyons, even if they can't be directly observed. One area of interest is in the study of neutrinos, which are known for their ability to pass through matter without interacting. In 2011, an experiment called OPERA made headlines when researchers thought they had detected neutrinos traveling faster than light, raising the possibility of tachyon-like behavior. However, further investigation revealed that the result was due to a measurement error, and the faster-than-light neutrinos were later disproven. Tachyons are also intriguing because of their potential connection to quantum mechanics and the strange behaviors observed at the quantum level. Quantum entanglement, for example, involves particles that can instantly affect each other's states, regardless of the distance between them. This spooky action at a distance, as Einstein called it, happens faster than light, at least in terms of information transfer. While quantum entanglement doesn't imply the existence of tachyons, it does show that certain aspects of the universe can operate outside the traditional limits of light speed. Tachyons, if real, could be part of this broader picture of faster-than-light phenomena in the quantum world. The potential dangers of tachyons, however, are not limited to their impact on our understanding of causality or space-time. If tachyons were somehow harnessed or created in a lab, they could introduce new forms of radiation or energy that we have never encountered before. Their faster-than-light motion might also give them the ability to interact with ordinary matter in strange and unpredictable ways, perhaps even destabilizing matter or causing destructive chain reactions. Dark matter candidates. Are we missing an invisible danger? Dark matter is one of the greatest mysteries in modern astrophysics. While it makes up about 27% of the mass-energy content of the universe, it has never been directly detected. Its presence is inferred from its gravitational effects on galaxies, galaxy clusters, and cosmic structures, but it remains invisible to all known forms of electromagnetic radiation. This invisible substance doesn't emit, absorb, or reflect light, making it undetectable by traditional observational methods. Despite being so elusive, the search for dark matter continues, driven by the possibility that understanding it could unlock a whole new aspect of the universe. One of the most compelling dark matter candidates is a type of particle known as a WIMP, or weakly interacting massive particle. WIMPs are theorized to have mass, but they barely interact with the matter that forms stars, planets, and even us. This weak interaction is why dark matter has managed to remain undetected despite its significant presence in the universe. The idea behind WIMPs is that they were created during the early moments of the universe, left over from the hot, dense conditions following the Big Bang. As the universe cooled, WIMPs became too cold and slow to annihilate each other, but they persisted in large quantities, becoming the dominant form of matter in the cosmos. This makes them prime candidates for dark matter, as they are massive enough to exert gravitational influence on galaxies, keeping them from flying apart, but elusive enough that they don't interact with light or other forms of radiation. The possible danger of WIMPs arises not from their current behavior, but from what could happen if they were ever detected or manipulated. Right now, they float through space, and even through us, without causing any harm. However, if advanced technology were developed that could detect or interact with WIMPs, it might trigger unforeseen consequences. WIMPs, by their very nature, could be interacting with the universe in ways that we don't yet understand. If these particles could be manipulated or concentrated, there could be risks that are difficult to predict. For instance, if large quantities of WIMPs were somehow brought together, could they create gravitational disturbances, affect the stability of ordinary matter, or even trigger unknown physical reactions? The search for WIMPs has been a major focus of experiments across the world. Many attempts to detect WIMPs involve underground laboratories, where scientists shield their detectors from cosmic rays and other forms of background radiation. These detectors are designed to capture the rare moment when a WIMP might interact with a normal particle, such as a nucleus, by imparting a small amount of energy to it. While no definitive detection has been made, the fact that WIMPs remain undetected has only deepened the mystery, suggesting that they may be even harder to find than originally thought. Another possibility is that dark matter is composed of primordial black holes. These would have formed in the earliest moments after the Big Bang, created by fluctuations in the density of the universe. Unlike traditional black holes, which are formed from the collapse of massive stars, primordial black holes could be much smaller, possibly even microscopic, but still have significant mass. While this theory is less popular than the WIMP hypotheses, it raises its own set of potential dangers. If primordial black holes exist in large numbers, they could occasionally pass through the solar system or even Earth, creating gravitational disturbances. A black hole the size of a grain of sand, for example, could pass through a planet without being noticed until its gravitational effects caused catastrophic damage. There is also the possibility that dark matter could be something even more exotic, like sterile neutrinos. A sterile neutrino would be even more elusive, not interacting with regular matter through any of the known forces except gravity. These particles could potentially account for dark matter, and they may be detectable through their influence on cosmic events, such as the behavior of stars and galaxies. If dark matter is stable and unchanging, then it may continue to be a silent partner in the cosmos, exerting its gravitational influence, but otherwise remaining inert. But if dark matter can be manipulated or concentrated, it may have properties that could cause unpredictable consequences. Since dark matter exists throughout the universe in such large quantities, it's possible that we have yet to see the full range of its effects. For example, could there be regions of space where dark matter density is higher, leading to increased gravitational forces that affect space travel, satellites, or even entire planets? Or could dark matter interact with regular matter in ways that are currently beyond our understanding, perhaps leading to energy releases or physical changes that we haven't yet observed? Weakly interacting massive particles, WIMPs, silent killers of the cosmos. WIMPs are thought to interact with regular matter only through the weak nuclear force and gravity, making them incredibly difficult to detect. These particles don't emit, absorb, or reflect light, which is why they remain invisible to telescopes and other detection devices. This weak interaction is also what gives them their name, weakly interacting massive particles. and it's the reason why they're still theoretical. Despite the difficulty in observing them, WIMPs are an appealing solution to the dark matter puzzle because they would explain many of the strange gravitational effects scientists have observed in the universe. The potential danger posed by WIMPs comes from their hypothetical abundance. If dark matter makes up around 85% of the total mass in the universe, and WIMPs are the leading candidate for dark matter, then we are surrounded by these particles at all times. They move through us, through the Earth, and through every other form of matter without causing harm, at least as far as we can tell. However, if the interaction between WIMPs and regular matter were to increase, even slightly, the consequences could be profound. While WIMPs currently appear to be benign, their mass and energy could have significant effects if these particles began to interact with normal matter more often or in unexpected ways. Imagine a scenario where WIMPs, for some reason, began to interact more energetically with regular matter. If WIMPs were able to impart significant amounts of energy to the atoms they collide with, this could lead to a chain reaction of sorts, where the nuclei of atoms in a material start to recoil more violently. In biological systems, such as the human body, this could damage DNA or other critical molecules, potentially leading to an increased risk of cancer or other diseases. WIMPs could also pose a danger if they were to accumulate in certain areas. While they pass through most matter without incident, there is a possibility that WIMPs could become trapped by gravitational forces, gathering in the cores of planets or stars. If enough WIMPs were to accumulate in one place, their combined gravitational influence could start to have noticeable effects on the surrounding matter. For instance, in the dense environment of a star or planet's core, WIMPs could interact with the nuclear fusion processes that power stars. One concerning possibility is that WIMPs could form dense clusters in the centers of black holes or neutron stars. In such extreme environments, the weak interactions that typically characterize WIMPs might become more significant. The intense gravity and high energy conditions inside these celestial objects could increase the likelihood of WIMP interactions, potentially leading to unknown consequences. Some researchers have speculated that if enough WIMPs were to gather in the core of a star, they could alter the star's life cycle, speeding up its death or even triggering a premature supernova. Currently, WIMPs are thought to play a critical role in holding galaxies together through their gravitational influence. Without dark matter, galaxies would not have enough mass to stay bound. They would fly apart under the influence of their own rotation. If WIMPs began to interact more frequently or more energetically with the matter in these galaxies, it could disrupt the delicate balance that allows galaxies to maintain their structure. The result could be a slow unraveling of galaxies, with stars and planets being thrown into new orbits or even ejected into intergalactic space. Exploring the idea that WIMPs could potentially become silent killers of the cosmos is an exercise that underscores how little we truly know about these particles. As scientists continue to search for WIMPs, one of the goals is to better understand the range of their interactions with regular matter. By learning more about how WIMPs behave, researchers hope to not only confirm their existence, but also assess whether they pose any long-term risks. If WIMPs are truly as weakly interacting as their name suggests, then they may remain a largely benign force in the universe, exerting only their gravitational influence on the matter around them. But if their interactions are more complex than we currently believe, then WIMPs could represent an ever-present, invisible source of danger. Axions, ghostly particles with colossal impact. Axions are another intriguing candidate for dark matter. These hypothetical particles are thought to be extremely light and weakly interacting, similar to WIMPs, but with even less impact on regular matter. The idea of axions comes from a problem in particle physics related to the strong nuclear force. Axions are different from many other particles because of their unusual characteristics. They're expected to be much lighter than electrons and interact so weakly with matter that they could pass through entire planets or stars without being affected or noticed. But their sheer abundance might compensate for their individual weakness. If axions make up dark matter, this vast population of axions could be scattered throughout galaxies, forming a kind of invisible web that holds galaxies together, influencing their movements and overall structure. One of the most compelling reasons why scientists think axions might exist is because they could solve a problem in physics known as the strong CP problem. The strong nuclear force, which holds atomic nuclei together, should theoretically allow for certain types of symmetry breaking that we don't observe in nature. Axions were proposed as a way to explain why this breaking doesn't happen, making them a very appealing theoretical particle. If axions exist, they could influence the behavior of stars. While stars are powered by nuclear fusion, the presence of axions in the regions around or within stars could subtly alter the energy balance. One of the concerns is that axions might carry away small amounts of energy from stars, potentially affecting their lifetimes. If axions are drawn into the cores of stars, they might act as a kind of invisible drain, pulling energy away and changing the processes that drive stellar evolution. While these effects would be small, over billions of years they could add up, potentially shortening the lives of stars or causing them to behave in unexpected ways. One of the most interesting aspects of axions is their potential to form axion stars. While normal stars are made of plasma and nuclear fusion, axion stars would be made entirely of axions, held together by their mutual gravitational attraction. These theoretical objects would be incredibly faint and hard to detect because axions don't emit light, but they could still exert a gravitational pull over nearby matter. Axion stars might lurk in the dark corners of the universe, slowly accumulating axions over time. If they exist, these strange objects could represent a new type of cosmic structure that we've never seen before. The potential dangers of axions, though largely speculative, stem from their interaction, or lack thereof, with regular matter. Because they are so weakly interacting, axions would not directly pose a threat to life on Earth or to our technology. But their influence on the large-scale structure of the universe could have long-term consequences. One concern that has been raised is whether axions, if they accumulate in large enough numbers, could disrupt the balance of forces in the universe. For example, if axions were to gather in the core of a galaxy, their gravitational influence might become strong enough to affect the orbits of stars or the overall shape of the galaxy. This could lead to changes in the distribution of matter within galaxies, potentially altering their long-term evolution. While these effects would likely be subtle, they could have a significant impact over cosmic timescales. Axions might also interact with magnetic fields in ways that could have observable consequences. Some theories suggest that axions could convert into photons, particles of light, when they pass through strong magnetic fields. This process, known as the axion-photon conversion, could allow axions to be detected indirectly by looking for unusual signals in areas with strong magnetic fields, such as around neutron stars or black holes. If axions can convert into photons, this could create new sources of radiation that might affect nearby planets or stars, though the likelihood of this happening is still uncertain. Magnetic monopoles, the cosmic time bombs. Another fascinating particle in physics is the magnetic monopole. Unlike the familiar magnetic dipoles that have both a north and a south pole, like the magnets we encounter in daily life, monopoles would have only one magnetic pole. Either they would be a pure north pole or a pure south pole, something that doesn't exist naturally in our current understanding of physics. However, many theories suggest that magnetic monopoles could have formed in the early universe, during the first fractions of a second after the Big Bang, when the universe was still extremely hot and dense. The idea of monopoles comes from the same branch of theoretical physics that gave us predictions about the existence of black holes and dark matter. Scientists believe that during the rapid expansion of the universe, known as cosmic inflation, magnetic monopoles could have been produced. They are hypothesized to be incredibly heavy and to carry a strong magnetic charge, which makes them stand out from regular particles. Their interactions with magnetic fields would be far more intense than the interactions we are familiar with when dealing with normal matter. If one of these monopoles were to pass through a magnetic field, it could disrupt the field in ways we have never seen before. Instead of the smooth interactions we observe between ordinary magnetic dipoles, monopoles would create ripples, distortions, and perhaps even lasting damage to the magnetic structures they encounter. One of the primary concerns about monopoles is the potential for them to destabilize magnetic fields, especially in cosmic environments. Magnetic fields are a crucial part of many astronomical systems, from the Earth's protective magnetosphere to the enormous magnetic fields found around stars, galaxies, and even black holes. These fields guide the movement of charged particles, including cosmic rays, and help protect planets like Earth from harmful radiation. The Earth's magnetic field, for example, is our primary defense against charged particles from the Sun, as well as cosmic rays from deep space. This protective bubble deflects many high-energy particles, preventing them from reaching the surface of the planet, where they could harm living organisms or damage electronic systems. If a magnetic monopole were to pass through the Earth's magnetosphere, the disruption it could cause would be catastrophic, weakening the field temporarily or creating localized collapses. Even a brief weakening of the magnetic field could lead to increased radiation exposure, potentially affecting satellites, power grids, and biological life. In space, the consequences of monopoles interacting with magnetic fields could be even more dramatic. Around stars and galaxies, magnetic fields play a role in the formation of cosmic jets, streams of charged particles that shoot out from the centers of galaxies or the regions around black holes at near light speeds. These jets are shaped and guided by magnetic fields, and if monopoles were present, they could disturb the dynamics of these streams, potentially altering their paths or intensity. The disruption could change how galaxies evolve, influencing the movement of matter and energy across the universe. In extreme cases, the interaction between monopoles and magnetic fields could lead to the creation of powerful bursts of radiation, similar to those seen in gamma-ray bursts or other high-energy cosmic events. If a monopole were to pass through a region with a strong magnetic field, the resulting collision could release an enormous amount of energy, potentially creating a localized burst of radiation that could spread across large distances. These bursts could have devastating effects on any planets, stars, or even entire solar systems caught in their path. Another possibility is that monopoles, if they exist in large numbers, could form massive structures in space. Since monopoles would only have one magnetic pole, they might attract each other in unique ways, potentially forming chains or clusters of monopoles that could act as cosmic time bombs. These structures might remain dormant for long periods, but if they were disturbed, perhaps by a passing star or a shift in the surrounding magnetic fields, they could release massive amounts of energy, triggering cosmic events that we have yet to observe. If monopoles exist, they are likely very rare, which makes them difficult to detect. Most theories suggest that the universe should be filled with many more magnetic monopoles than we've observed, which has led scientists to wonder why we haven't seen them yet. Some researchers speculate that monopoles could be hiding in places where we haven't looked, or that they might be trapped in regions of space where their effects are minimized. Experiments using particle accelerators, such as the Large Hadron Collider, are searching for signs of monopoles by smashing particles together at incredibly high speeds. If they exist, these high-energy collisions might produce them, allowing researchers to study their properties directly. Other experiments are looking for signs of monopoles in cosmic radiation, hoping to detect the telltale signs of their interactions with magnetic fields in space. The discovery of magnetic monopoles would revolutionize our understanding of physics. Not only would it confirm a long-standing prediction of many theories in particle physics, but it would also provide new insights into the fundamental forces that govern the universe. Monopoles could help explain how the universe evolved after the Big Bang, offering clues about the early stages of cosmic inflation and the formation of large-scale structures like galaxies and galaxy clusters. But with this discovery could come new dangers. Could they destabilize magnetic fields in ways we haven't anticipated? Could they trigger cosmic events that pose a threat to life or technology? False vacuum decay, the threat of the universe's instant collapse. False vacuum decay is one of the most unsettling ideas to come out of modern physics. It suggests that the universe, as we know it, might not be in its most stable state. Instead, we could be living in what's known as a false vacuum, a state that feels stable but is in fact teetering on the edge of a catastrophic collapse. If the universe is indeed in this delicate state, all it would take is a tiny fluctuation, a single event, to trigger the collapse of everything. This collapse wouldn't happen slowly over time, but would instead spread at the speed of light, annihilating the universe in an instant. The idea of vacuum decay arises from quantum field theory, which is a framework physicists use to describe the behavior of particles and forces on a fundamental level. In quantum field theory, every particle has a corresponding field that fills the entire universe. These fields can exist in different energy states, and the universe itself is thought to have an overall energy level. The lowest possible energy state is called a true vacuum, and this is where the universe should naturally want to be, a state of complete stability. However, if the universe is in a false vacuum, it means we're in a local minimum of energy, rather than the absolute minimum. To understand this, imagine the universe as a ball resting in a shallow dip on a hilly landscape. The ball isn't at the bottom of the hill, where it would be completely stable, but it's stuck in this dip, unable to roll up the hill to reach the true bottom. From where it sits, the ball appears stable, but a small push could send it rolling down to the true vacuum, the most stable state, where it would settle once and for all. That push, in the case of false vacuum decay, could be caused by a random quantum fluctuation, or a high-energy event that forces the universe out of its current state. What makes this scenario even more unsettling is the possibility that this collapse could begin at any moment, anywhere in the universe. If a quantum fluctuation was strong enough to kick a small region of space out of the false vacuum, that region would rapidly expand, converting everything in its path. This bubble nucleation is one of the most unsettling aspects of false vacuum decay. It involves the formation of a bubble in space where the energy state drops to a lower, more stable level than the surrounding universe. This bubble is essentially a region of true vacuum, representing the ultimate low-energy state. Outside the bubble, the universe remains in the false vacuum, a less stable state that is only temporarily holding together. But once the bubble forms, it sets off a chain reaction that spreads outward at the speed of light, reshaping everything in its path as it converts the false vacuum into the true vacuum. This bubble expansion doesn't happen slowly. It spreads outward at the speed of light, which means there's no way to outrun or escape it. As the bubble grows, it consumes everything in its path. The transition from false vacuum to true vacuum isn't just a minor adjustment. It's a fundamental shift in the nature of the universe itself. The forces that govern everything from the behavior of particles to the structure of galaxies would be altered. Inside the bubble, the laws of physics would be different, and the fabric of space and time could be reshaped in ways that are difficult to predict. This concept of false vacuum is rooted in serious physics and has been discussed by some of the leading minds in the field, including Stephen Hawking. The Higgs field, which is associated with the Higgs boson particle, is one of the fields that might determine whether the universe is in a true or false vacuum. The properties of the Higgs boson, specifically its mass, play a crucial role in this discussion. Some calculations suggest that the current mass of the Higgs boson is consistent with a universe that's in a metastable state, a false vacuum. If this is true, it means that the Higgs boson is telling us that while the universe has been stable for billions of years, it's not guaranteed to remain that way forever. The timescales involved are enormous, potentially far longer than the current age of the universe, but the fact remains. There's a possibility, however small, that the universe could suddenly collapse into a more stable state at any time. What causes this apocalyptic bubble nucleation chain reaction? According to quantum field theory, the fields that fill the universe can fluctuate in unpredictable ways. Occasionally, these fluctuations can be large enough to push a region of space from the false vacuum into the true vacuum. This process is known as quantum tunneling, and while it's incredibly rare, it's not impossible. In theory, all it takes is one sufficiently large fluctuation to nucleate a bubble of true vacuum. Once this bubble forms, the decay of the false vacuum is inevitable. The energy difference between the false vacuum and the true vacuum plays a critical role in driving the expansion of the bubble. The greater the energy difference, the faster the bubble expands and the more violent the transition. When the bubble of true vacuum forms, the energy released by the collapse of the false vacuum is converted into kinetic energy, driving the rapid expansion of the bubble's walls. As the bubble grows, it sweeps through space, leaving behind a new, lower energy reality. Anything caught in the path of this expanding bubble is obliterated, and the structure of matter itself could be altered beyond recognition. Some scientists have likened the expansion of a vacuum bubble to the detonation of a bomb, albeit on a cosmic scale. Instead of a localized explosion, the entire universe would be caught up in this process of transformation. The energy released in this transition would be enough to destroy stars, planets, and galaxies. Even the fundamental particles that make up matter might not survive the shift to the true vacuum. The vacuum decay process wouldn't just be catastrophic in terms of physical destruction. It would represent a complete reset of the universe's underlying structure. Unlike other cosmic threats, such as asteroid impacts or gamma-ray bursts, where we might imagine ways to protect ourselves or mitigate the damage, false vacuum decay is beyond our control. It's a fundamental shift in the structure of the universe, driven by the deepest laws of physics. Once the process begins, it's unstoppable. A disturbing possibility is that the process of vacuum decay could already have begun somewhere in the universe, and we just don't know it yet. Because the bubble of true vacuum travels at the speed of light, it could be expanding toward us right now, but we wouldn't see it coming. The light from distant galaxies would continue to reach us until, suddenly, everything was gone. There would be no time to react, no warning signs, just instant annihilation. Despite how terrifying this idea sounds, it's worth noting that the odds of false vacuum decay happening anytime soon are incredibly small. The universe has existed for over 13 billion years without any sign of such a collapse. And most models suggest that, if it ever does happen, it's more likely to occur on timescales much longer than the current age of the universe. However, because we don't fully understand all the details of quantum field theory, there's still a degree of uncertainty about how likely this scenario is. Scientists are continuing to study the properties of the Higgs field and other factors that could influence whether the universe is in a true or false vacuum. By improving our understanding of these fundamental forces, researchers hope to get a clearer picture of the universe's long-term stability. Some speculate that future advancements in particle physics could allow us to fix the false vacuum problem, offering us a small ray of hope. The GZK cutoff. Why the highest energy cosmic rays confound us. The Grayson-Zatsepin-Kuzmin limit, named after Kenneth Grayson, Vadim Kuzmin, and Georgy Zatsepin, is a theoretical limit on the energy that cosmic rays can have when traveling through space. According to their theory, cosmic rays with energies above a certain threshold should lose energy over time as they interact with the cosmic microwave background, or CMB, a sea of low-energy photons that fills the universe. This interaction causes the cosmic rays to gradually slow down and lose their extreme energy, meaning that, in theory, any cosmic ray that has traveled a great distance should have an energy below this limit, which is also known as the GZK cutoff. The GZK cutoff, which has a value of around 5 times 10 to the power of 19 electron volts, marks the point at which cosmic rays are expected to start losing energy significantly due to collisions with CMB photons. When a high-energy cosmic ray interacts with these photons, it can produce new particles, such as pions, which drain some of the cosmic ray's energy. This energy loss becomes more pronounced for cosmic rays that have traveled vast distances from their source, which should result in a clear upper limit on the energy that cosmic rays can have by the time they reach Earth. However, despite this well-established theoretical limit, scientists have observed cosmic rays that exceed the GZK cutoff. These UHECRs defy the expected energy limits, posing a significant puzzle for physicists. If cosmic rays lose energy as they travel through the universe, how can we detect particles with energies beyond this threshold? Where do these particles come from, and what allows them to retain such extreme energy levels? One possible explanation is that these UHECRs are produced by sources that are relatively close to Earth. If a cosmic ray is created within about 100 million light-years of our planet, it may not have had enough time to lose significant energy through interactions with the CMB. In this case, the cosmic ray could still reach Earth with an energy above the GZK cutoff. This would imply that the sources of these high-energy particles are relatively nearby in cosmic terms, potentially involving violent astrophysical phenomena like gamma-ray bursts, supermassive black holes, or active galactic nuclei. However, this explanation presents its own challenges. Despite the proximity of potential sources, identifying them has proven difficult. The trajectories of cosmic rays are influenced by the magnetic fields they pass through as they travel across the universe. These fields bend the paths of cosmic rays, making it hard to trace them back to their origin. The more energetic the cosmic ray, the less it is deflected by magnetic fields. But even the slight bending caused by these fields complicates efforts to pinpoint where UHECRs are coming from. Another theory is that there may be unknown or exotic processes at work that allow cosmic rays to exceed the GZK cutoff. For example, some researchers have speculated that these UECRs could be produced by hypothetical objects like topological defects or decaying super-heavy particles from the early universe. These objects, if they exist, could release enormous amounts of energy when they break apart, accelerating particles to extreme velocities and sending them across the universe. Topological defects are structures that could have formed during the universe's early moments. They might include cosmic strings, domain walls, or monopoles, objects that are theorized to hold immense energy. If cosmic rays are produced by interactions involving these defects, they might be able to reach Earth with energies beyond the GZK cutoff, even if they come from faraway regions of the universe. However, no direct evidence for topological defects has been found so far. The existence of UHECRs above the GZK cutoff also raises the possibility that our understanding of cosmic ray interactions with the CMB could be incomplete. Perhaps there are subtleties in how high-energy particles interact with photons that we haven't yet discovered. Alternatively, there may be features of the CMB itself that haven't been fully accounted for, such as variations in its intensity or structure on very small scales, which could affect how cosmic rays lose energy over time. UHECRs exceeding the GZK cutoff go beyond just a theoretical curiosity. Cosmic rays with such extreme energies carry an immense amount of energy in a single particle. While the Earth's atmosphere provides significant protection against cosmic rays, especially for particles with lower energies, UHECRs are so energetic that they can penetrate deeper into the atmosphere, creating more intense particle showers that could potentially have harmful effects on high-altitude aircraft, satellites, or astronauts in space. One of the goals of cosmic ray research is to build a complete map of the sky that traces the trajectories of UHECRs back to their sources. This would help scientists understand what kinds of cosmic events are responsible for these extreme particles and how they manage to exceed the GZK cutoff. However, achieving this goal requires overcoming the challenges posed by magnetic fields, cosmic distances, and the limited number of UHECRs detected each year, Muon showers, Earth's natural particle colliders. We've discussed the formation of air showers when cosmic rays collide with Earth's atmosphere. Among the particles produced during air showers are muons, heavy cousins of the electron. Muons are unique because they have a much greater mass than electrons, about 200 times heavier, and they are relatively stable compared to many other particles formed in these high-energy interactions. While most of the particles in cosmic ray showers quickly decay or lose energy, muons can travel much farther, penetrating deep into Earth's atmosphere and even reaching the surface. Muons are an important part of the radiation that constantly bombards Earth from space, and they play a key role in particle physics research. Their ability to penetrate matter makes them useful for probing dense materials in a variety of applications. However, their presence also raises questions about the potential dangers they pose to both technology and biology, particularly when large numbers of muons are generated in high-energy cosmic ray showers. Muons are produced when cosmic rays, usually protons or atomic nuclei, collide with the nuclei of atoms in the upper atmosphere. These high-energy collisions create pions and kaons, which are short-lived particles that quickly decay into muons and neutrinos. Because of their high energy and mass, muons can travel through tens or even hundreds of meters of rock or other materials before interacting with matter or decaying. This makes them one of the most penetrating forms of cosmic radiation that reaches Earth's surface. Despite their ability to pass through dense materials, muons are not directly harmful to humans in the small amounts that naturally occur. The average person is exposed to muons constantly, without any noticeable effects. On the surface of the Earth, about 1 muon passes through each square centimeter of our bodies every minute. While this may sound alarming, the energy deposited by these muons is generally not enough to cause any immediate harm. Humans have evolved to live with a low level of background radiation, including the radiation from cosmic rays and the muons they produce. However, in larger numbers, muons could potentially pose a threat, particularly in environments where they accumulate or where there are frequent high-energy cosmic ray events. Muons can ionize atoms in materials as they pass through, which can lead to the creation of electron-hole pairs in semiconductors. This ionization can cause temporary or permanent malfunctions in electronic devices. The deeper penetration of muons means that they can reach sensitive components shielded from other forms of cosmic radiation. At higher altitudes, the number of muons increases significantly because the cosmic ray showers have not had as much time to dissipate before reaching these levels. This can lead to higher doses of radiation for passengers and crew, which may have health implications over long periods of time. While the radiation dose from muons alone is not enough to cause immediate harm, it can contribute to the overall radiation exposure experienced by people in these environments. Over the years, scientists have developed techniques to use muons to peer inside large or dense objects, a process known as Muon tomography. This technique takes advantage of the fact that muons can pass through materials that would stop other particles, making them ideal for scanning the interiors of structures like volcanoes, pyramids, or even nuclear reactors. By detecting the number of muons that pass through different parts of an object, researchers can create images of its internal structure, much like an X-ray. The biological effects of increased muon exposure are still a subject of research. While the low-level background of muons we experience daily is not harmful, a significant increase in muon flux could potentially cause damage to living cells. Muons, like other forms of ionizing radiation, can break chemical bonds in DNA, while the likelihood of such events occurring is small. Understanding the potential risks is important for both space exploration and our understanding of cosmic radiation's impact on life on Earth. Cherenkov radiation, the blue glow of superluminal particles. Cherenkov. Radiation is a fascinating phenomenon that occurs when a charged particle travels through a medium at a speed greater than the speed of light in that medium. While this might seem counterintuitive, it's important to note that the speed of light in a vacuum is a universal constant. But light travels more slowly through other materials, like water or glass. When a particle, usually an electron, exceeds the local speed of light in such a medium, it creates a distinctive blue glow, which is known as Cherenkov radiation. This radiation is more than just an aesthetic feature of high-energy physics. It can signal the presence of extremely fast and potentially dangerous particles. The blue glow of Cherenkov radiation is often associated with nuclear reactors. Inside these reactors, subatomic particles like electrons are sometimes accelerated to high speeds by the nuclear reactions occurring within. As they move through the water that surrounds the reactor core, they can exceed the speed of light in that water. The result is a pale blue light, often seen in photographs of reactors, that signals the presence of particles moving at near light speeds. Cherenkov radiation is not limited to reactors, though. It also appears in natural settings, particularly when cosmic rays or other high-energy particles collide with Earth's atmosphere or pass through other dense mediums. This radiation is a useful tool for astrophysicists studying the behavior of cosmic rays and their impact on Earth, as it offers a direct way to observe the interaction of these particles with the environment. The creation of Cherenkov radiation plays a crucial role in particle detectors, especially in experiments that involve high-energy physics. These detectors are often filled with materials like water or specialized fluids that slow down the speed of light. When a high-energy particle enters the detector, if it is moving fast enough, it will produce Cherenkov radiation, signaling its passage through the medium. This blue light provides scientists with a method to detect particles that would otherwise be invisible, allowing them to track the movement and speed of these elusive particles. One of the most well-known applications of Cherenkov radiation detection is in neutrino observatories. On the rare occasion where a neutrino interacts with a particle in a dense medium like water or ice, it can produce a high-speed charged particle, such as an electron, that travels faster than light in that medium. The resulting Cherenkov radiation can be detected by observatories, like the IceCube Neutrino Observatory in Antarctica. By observing the pattern of Cherenkov light, scientists can determine the direction and energy of the incoming neutrino, providing valuable data about these ghostly particles. But Cherenkov radiation also highlights the dangers that come with particles traveling at such high speeds. When particles exceed the speed of light in a medium, they can deposit large amounts of energy into their surroundings, ionizing atoms and disrupting molecular structures. This energy deposition can cause significant damage to materials, particularly sensitive electronics or biological tissues. Particle jets from quasars, dangerous beams from the distant universe. Quasars are among the most energetic objects in the universe. Located at the centers of distant galaxies, these extraordinarily bright beacons are powered by supermassive black holes that draw in vast amounts of matter. As gas, dust, and other material fall toward the black hole, they form a swirling disk, called an accretion disk, which becomes intensely hot. The energy released from this process can outshine the entire galaxy surrounding the quasar. But beyond their incredible brightness, quasars are known for something even more dramatic: powerful jets of particles that shoot out from their centers at near-light speeds. These particle jets are among the most extreme phenomena observed in the universe, and their potential impact extends far beyond the galaxy in which the quasar resides. The jets can stretch across vast distances, spanning thousands or even millions of light years, carrying with them enormous amounts of energy. While these jets may appear distant and harmless from our point of view on Earth, the reality is that if a planet or other object were to be in the path of one of these jets, the consequences would be apocalyptic. The formation of these jets begins in the heart of the quasar, where the immense gravitational pull of the black hole draws in matter. As the material spirals inward, it doesn't fall straight into the black hole. Instead, the intense pressure and magnetic fields in the accretion disk cause some of the material to be funneled into two narrow jets that shoot out from the poles of the black hole. These jets are composed of highly energetic particles, primarily electrons and protons, but they may also contain heavier particles, as well as high-energy photons, including gamma rays. The jets are tightly focused into narrow beams and can travel at nearly the speed of light. This makes them incredibly dangerous, as the particles within the jet carry enormous energy. If one of these jets were to strike a planet, the particles could tear through its atmosphere, generating lethal levels of radiation. Even without a direct hit, the sheer energy of the jets could cause widespread damage to any objects in their vicinity. Because they are so tightly focused and move so quickly, the jets can remain concentrated for millions of light years, affecting regions far from their source. While it's highly unlikely that the Earth will be in the direct path of a quasar's jet, since most quasars are located in the distant universe, a tiny possibility remains that in some distant future, our planet or a nearby celestial object could be impacted by such a beam. In addition to the particles themselves, the radiation emitted by these jets presents another layer of danger. Quasars emit electromagnetic radiation across a wide range of wavelengths, from radio waves to gamma rays. The gamma rays in particular are of concern because they are among the most energetic forms of light and can penetrate deep into objects they strike. Gamma radiation is known to strip away the protective ozone layer, which shields the planet from harmful ultraviolet rays from the sun. Without this protection, life as we know it would be exposed to intense radiation, causing widespread extinction. The potential dangers of quasar jets aren't limited to distant planets. Quasars are found in galaxies far from our own, but they are also part of a broader family of objects known as active galactic nuclei, or AGN, which includes closer galaxies with similar, though less extreme, energetic processes. Some AGN also produce particle jets, and while they may not be as powerful as those from quasars, they can still pose significant risks to objects in their path. Quasars are not constant emitters of particle jets. They can flare up and become more active over time, increasing the intensity of their jets. These flares can be triggered by a variety of factors, including interactions with other galaxies or changes in the flow of matter into the black hole. When a quasar becomes more active, its particle jets can become more powerful, potentially reaching new regions of space and affecting objects that were previously outside of their influence. The jets are often accompanied by intense magnetic fields, which can interact with the magnetic fields of nearby objects, including planets or stars. These interactions can lead to a variety of effects, from altering the behavior of a planet's atmosphere to triggering geomagnetic storms that could disrupt technological systems on a global scale. The jets also have the potential to alter the structure of the galaxy itself. As the jets plow through interstellar space, they can push away gas and dust, preventing new stars from forming in certain regions of the galaxy. This can have long-term effects on the evolution of the galaxy, potentially reducing the number of new stars and planets that form over time. In extreme cases, the jets can even blow gas out of the galaxy entirely, stripping away the material needed for future star formation. The universe's ultimate particle accelerator, the large-scale structure of space. The universe is vast, and its structure is anything but random. Over billions of years, galaxies have coalesced into intricate webs of matter stretching across enormous distances. Scientists call the large-scale structure. This structure consists of filaments, long strands of galaxies and gas, and voids, which are massive regions of empty space. Together, they create a kind of cosmic skeleton, a framework imaginable. But beyond being just a cosmic blueprint, this structure might also function as an enormous particle accelerator. Particles to unimaginable energies and amplifying the dangers they pose. Cosmic filaments, the dense thread-like formations that connect galaxy clusters, are thought to contain vast amounts of matter and magnetic. As particles pass through these filaments, They may encounter magnetic fields that twist and accelerate them, much like how particle accelerators on Earth use electromagnetic fields to propel particles to near-light speeds. The difference here, of course, is the scale. Filaments can stretch for hundreds of millions of light years, providing a long runway for particles to gain energy. Over these distances, particles could be accelerated to energies that are simply impossible to replicate on Earth, entering realms of physics that are still largely unexplored. The voids of the universe, those massive empty regions between filaments, also play a role in this natural acceleration process. While they are called voids because they are relatively empty, these vast regions are not completely devoid of. In fact, they contain a faint but crucial presence of dark matter and sparse hydrogen gas. Particles passing through voids could be affected by the gravitational pull of dark matter, pulling them across these empty expanses and speeding them up as they go. Additionally, the lack of resistance in these voids, because they are mostly empty space, means particles can travel for long periods without being slowed down or disrupted, allowing them to maintain or even increase their high energies. This large-scale acceleration process could explain why scientists observe cosmic rays exceeding the GZK cutoff. In addition to directly accelerating particles, the large-scale structure could influence how particles interact with each other. In regions where filaments and voids intersect, the density of matter and energy changes dramatically, creating zones of instability. These areas of transition could act as sites where high-energy particles are more likely to collide with other particles or energy fields. When particles collide at such extreme energies, they can produce secondary particles, gamma rays, or other forms of radiation that can spread across vast distances, potentially threatening any nearby planetary systems. One possible danger is the production of gamma-ray bursts, or GRBs, which are among the most energetic events in the universe. GRBs are already a known risk to life. A single burst directed at Earth from a relatively close distance could strip away our atmosphere and cause mass extinctions. If the large-scale structure of the universe helps to accelerate particles and trigger more frequent or more powerful GRBs, the risk of these catastrophic events might be much greater than previously thought. Another danger lies in the potential for magnetic reconnection events within these cosmic structures. Magnetic reconnection is a process where magnetic fields realign and release large amounts of energy. It happens on a much smaller scale in places like the Sun, where it can lead to solar flares and coronal mass ejections that can affect Earth's technology. On a cosmic scale, magnetic reconnection events within filaments or other structures could release even more energy, potentially creating particle jets or other high-energy phenomena that could affect nearby galaxies or systems. Could cosmic strings produce dangerous particle emissions? Cosmic strings are hypothetical, one-dimensional defects in space-time, which, if they exist, are believed to stretch across vast distances, perhaps even the entire universe. These strange objects are thought to have formed in the early moments after the Big Bang, when the universe was still a seething mass of high-energy particles and forces, rapidly expanding and cooling. As the universe cooled, various forces that were once unified began to separate, a process theorists compare to the cooling of water into ice. In some models, this process might have left behind cosmic strings, essentially cracks or defects in space-time. If these objects truly exist, they could be sources of incredibly intense energy and particle emissions. Their unique properties as defects in space-time would allow them to generate massive gravitational and electromagnetic forces, which could produce streams of high-energy particles capable of causing large-scale destruction. Theoretical models suggest that cosmic strings would be immensely thin, but incredibly dense. A single cosmic string could have a mass comparable to an entire star compressed into a strand thinner than an atomic nucleus. The tension within these strings would be astronomical, as the defects would be under immense pressure from the fabric of space-time itself. This tension could lead to violent interactions with anything they encounter, including stars, planets, and even galaxies. One of the most dangerous ways cosmic strings could interact with their surroundings is through the emission of gravitational waves. As cosmic strings move and vibrate through space, they could form kinks or loops, which would radiate gravitational waves, ripples in spacetime that travel at the speed of light. These waves carry energy away from the cosmic strings, and while gravitational waves themselves are not directly harmful, the energy emitted through this process could have indirect consequences. For instance, if a cosmic string passed near a planet or star, the intense gravitational waves could disturb or even destabilize the objects in its vicinity, potentially leading to catastrophic consequences, such as planetary collisions or stellar explosions. In addition to gravitational waves, cosmic strings might also emit particles, especially when they interact with other cosmic strings or matter. If two cosmic strings were to collide or cross paths, they could snap or form loops, releasing immense amounts of energy. These interactions could cause the emission of high-energy particles, including cosmic rays, gamma rays, and other forms of radiation that could spread across the universe. In such a scenario, the burst of particles could behave much like the energetic jets emitted by quasars, or the shock waves produced by supernovae, creating zones of intense radiation that could be deadly to any life forms or technology in their path. What makes cosmic strings particularly concerning is the fact that, unlike other known astronomical objects, they could cut across vast distances without interacting with most matter. Due to their incredibly small width, cosmic strings could pass through planets, stars, and even entire galaxies without being significantly slowed down or disrupted. However, while their width might allow them to avoid direct interaction with matter, their gravitational and particle emissions could still pose a serious threat. If a cosmic string passed near Earth, for example, the gravitational waves or particle streams it generated could disrupt the planet's magnetic field. As cosmic strings stretch and vibrate, they could, under the right conditions, act as a sort of cosmic particle accelerator. The intense gravitational forces surrounding a cosmic string could create pairs of particles and antiparticles by converting energy into mass through processes similar to those that occur in particle colliders. These pairs of particles could then be released into space, where they would either annihilate each other, releasing even more energy, or spread across the universe as high-energy cosmic rays. UHCRs could be the result of interactions between cosmic strings and matter. Another possible danger comes from the theoretical prediction that cosmic strings could cause cosmic vortices, whirlpools of energy and particles that could form around the strings as they move through space. These vortices could trap particles, including dangerous high-energy particles, and concentrate them in certain regions. If a cosmic vortex formed near a star or planet, it could funnel high-energy particles toward the object, intensifying the radiation exposure and increasing the risk of damage. Finally, there is the possibility that cosmic strings could destabilize spacetime itself. As defects in the fabric of spacetime, cosmic strings are thought to represent a kind of crack in the universe's structure. While the effects of such defects are not fully understood, it is possible that they could lead to distortions in the laws of physics in their vicinity. These distortions could alter the behavior of particles, energy, and even gravity, creating unpredictable and potentially dangerous effects. If cosmic strings were to cause localized instabilities in spacetime, the resulting disturbances could have wide-reaching consequences, potentially leading to the collapse of nearby structures, or even triggering more fundamental changes in the universe's physical laws. Dark photons, the hidden carriers of cosmic destruction. Last but not least, dark photons are hypothetical particles that could act as a bridge between regular matter and dark matter. In this sense, dark photons could carry energy within the dark sector of the universe, but in ways that might still affect the known universe. Their potential to interact with dark matter, and possibly ordinary matter, could lead to consequences that we don't yet understand. The concept of dark photons stems from the idea that dark matter might not be entirely silent. While dark matter doesn't interact with light or other electromagnetic radiation, the theory of dark photons suggests that dark matter could have its own form of electromagnetic force mediated by these dark photons. If dark matter has a hidden force, similar to the way electromagnetism works in our visible universe, dark photons would be the particles carrying that force. These dark photons would, in theory, move through the universe largely unnoticed by our instruments, since they wouldn't interact with regular photons. But if the conditions were right, they could still have subtle interactions with normal matter, transferring energy or creating disturbances in the fabric of space-time. One of the biggest questions about dark photons is whether they can exchange energy between dark matter and regular matter. If they can, dark photons could serve as a gateway for energy transfer across different sectors of the universe. This idea leads to the unsettling possibility that energy from the dark sector might occasionally be funneled into our visible universe in ways that we can't yet predict or detect. If that energy is carried by dark photons, it could appear suddenly, without warning, altering the behavior of particles and forces in ways that could have catastrophic consequences. To understand the potential danger dark photons pose, consider the ways regular photons interact with matter. In the form of light, radiation, and other electromagnetic phenomena, photons are responsible for many of the physical processes we observe. They heat up objects, transfer energy between particles, and can even destroy molecular structures through ionizing radiation. Dark photons, if they exist, could have similar effects on dark matter, but if they can interact with regular matter under certain conditions, they might carry harmful energy into areas of space that were previously unaffected. The result could be waves of destruction in regions exposed to this hidden form of radiation. Stars are powered by nuclear fusion, a delicate balance between gravitational forces and the pressure generated by fusion reactions in their cores. If dark photons were to transfer energy into a star's interior, they could disrupt this balance, leading to premature stellar collapses or even causing stars to explode as supernovae before their time. Such an event could have catastrophic effects, both for nearby planets and for the surrounding cosmic environment, releasing intense radiation and particles across vast distances. If they carry energy that interacts with dark matter, they could influence the distribution of dark matter in and around galaxies. Since dark matter plays a key role in holding galaxies together through its gravitational pull, any disturbances in dark matter's behavior could lead to shifts in the overall structure of galaxies. Galaxies could become destabilized, their stars drifting apart or collapsing inward as dark matter is affected by these unseen forces. Such disruptions might not be immediately noticeable, but over long periods, they could drastically change the landscape of the universe. Additionally, if dark photons are capable of interacting with regular photons under certain conditions, they could create phenomena similar to what we see with regular electromagnetic radiation. For instance, dark photons might be able to cause bursts of dark radiation, which could travel through space much like gamma-ray bursts, but in a form we cannot easily detect. If these bursts were to cross paths with regular matter, they might suddenly dump enormous amounts of energy into an area, causing intense radiation damage or particle accelerations that could destroy everything in their vicinity. Unlike regular photons, which we can see and measure with our telescopes and sensors, dark photons could be moving through the universe right now, influencing particles and forces in ways we don't yet understand. Their interactions with regular matter might be so rare or so subtle that we have no way of knowing when or where they will occur. This unpredictability makes them especially dangerous, as their effects could strike without warning, leaving devastation in their wake. The limits of human shielding. Can we protect ourselves from cosmic threats? Humanity has always looked to the stars with a sense of wonder and curiosity, but as we learn more about the universe, we also discover its dangers. Space exploration and even life on Earth can be threatened in countless ways by a vast variety of high-energy particles traveling through space. Cosmic rays, gamma rays, and other energetic particles can pose serious risks to astronauts, satellites, and infrastructure on Earth. Astronauts are particularly vulnerable to cosmic rays and other high-energy particles. When traveling beyond Earth's protective magnetic field, such as on missions to the Moon or Mars, they are exposed to a constant bombardment of radiation. This radiation can penetrate the skin, damaging DNA and increasing the risk of cancer, radiation sickness, and other health problems. Current spacecraft use shielding made from materials like aluminum to protect astronauts, but these materials can only stop a fraction of the harmful radiation. High-energy particles like cosmic rays can pass through most materials with ease, making it difficult to provide complete protection. In recent years, scientists and engineers have explored different ways to improve radiation shielding for space missions. One approach is to use materials that are better at absorbing or deflecting high-energy particles. For instance, hydrogen-rich materials like polyethylene are more effective than metals like aluminum at stopping cosmic rays. This is because hydrogen atoms, with their single proton, can slow down incoming particles through collisions, reducing the amount of radiation that reaches astronauts. Some researchers have proposed using water, or even the astronaut's own waste, as a shielding material, placing these substances around the crew compartment to create a protective barrier. Another idea involves creating magnetic or electric fields to deflect cosmic rays away from spacecraft. Earth's magnetic field provides a natural shield against many of the charged particles that reach our planet, and scientists are exploring whether similar fields could be generated around spacecraft to mimic this protection. Magnetic shielding would involve creating a strong enough field to bend the paths of cosmic rays and other charged particles, steering them away from the astronauts. However, the power requirements for such a system would be immense, and the technology to create portable magnetic fields of this strength is still in its infancy. One of the biggest challenges with shielding in space is that not all cosmic threats are the same. High-energy particles come in many forms, and no single material or method can protect against all of them. For example, while hydrogen-rich materials may be good at stopping protons and other lighter particles, they are less effective against heavier atomic nuclei, which make up a significant portion of cosmic rays. These heavier particles, known as high atomic number and energy, or HCE particles, are particularly dangerous because they can cause more severe damage when they collide with human tissue or spacecraft materials. 10. The problem of shielding becomes even more complicated when we consider other cosmic threats, like gamma rays and X-rays. These types of radiation are much harder to block than cosmic rays because they are made up of photons, which have no mass and can pass through many materials with ease. To stop gamma rays, extremely dense materials like lead or thick layers of concrete are needed. This presents a major obstacle for space missions, where weight is a critical factor, and it would be impractical to carry heavy shielding materials on long journeys. On Earth, we are mostly protected from cosmic rays and other forms of radiation by our atmosphere and magnetic field. However, even here, the rise of space-based technologies and infrastructure has increased the need for better protection against cosmic threats. Satellites, for instance, are constantly exposed to radiation in space, and over time, this can degrade their electronic components, causing malfunctions or even complete failures. To protect satellites and other space infrastructure, engineers have developed radiation-hardened electronics that are more resistant to the effects of high-energy particles. These components use special materials and designs to minimize damage from radiation, but they are not foolproof, and there is always the risk that a particularly strong burst of cosmic rays could overwhelm these defenses. Cosmic radiation will also significantly impact future human habitats on the Moon, Mars, or other planets. Without Earth's atmosphere and magnetic field, these environments are bathed in radiation, and any long-term human presence will require advanced shielding to protect against the constant bombardment of high-energy particles. One proposal is to build habitats underground or cover them with a thick layer of regolith, the loose soil and rock that covers the surface of the Moon and Mars. This natural material could provide some protection by absorbing or scattering incoming radiation, much like Earth's atmosphere does. However, creating large, livable spaces underground would be a significant engineering challenge, and it remains to be seen whether this approach will be practical. It is clear that new innovations in shielding technology are needed to protect both astronauts and infrastructure from the dangers of cosmic particles. One area of research that shows promise is the development of active shielding systems, which would use electromagnetic fields or other technologies to constantly adjust the level of protection based on the surrounding radiation environment. These systems could provide dynamic shielding that adapts to different types of particles and radiation, offering better protection than passive materials like aluminum or polyethylene. Another possibility is the use of nanotechnology to create new materials that are more effective at stopping high-energy particles. Scientists are exploring the use of carbon nanotubes and other nanomaterials to develop lightweight, flexible shielding that could be applied to spacecraft, habitats, and even spacesuits. These materials could provide better protection by absorbing or deflecting incoming particles at the molecular level, reducing the amount of radiation that reaches astronauts or sensitive equipment. No matter how advanced our technology becomes, it may never be possible to completely eliminate the risks posed by cosmic rays, gamma rays, and other high-energy particles. Even the most advanced shielding systems will likely only reduce, not eliminate, the threat. The cosmic ray spectrum, a puzzle of extreme energies. When we discussed cosmic rays earlier, I mentioned that they come in a wide energy range. At the lower end of this energy spectrum, cosmic rays carry modest amounts of energy, similar to the energy carried by particles produced in human-made accelerators, like those at CERN. These lower energy cosmic rays are well understood, and their sources are thought to include the Sun, supernovae, and other relatively common cosmic events. However, as we move up the spectrum toward higher energies, things become much less clear. One of the main mysteries of the cosmic ray spectrum is why some cosmic rays have such extreme energies. Cosmic rays with energies above a certain threshold, known as the Ni in the spectrum slope, are particularly intriguing. At this point, the energy of the cosmic rays takes a noticeable jump, and their origin becomes harder to explain using known astrophysical sources. These high-energy cosmic rays are thought to come from more violent and energetic processes than their lower-energy counterparts, but the exact mechanisms responsible for accelerating these particles to such extreme velocities are still poorly understood. Some scientists believe that cosmic rays with energies above the Ni are the result of events such as supernovae, the explosive deaths of massive stars. When a supernova occurs, it releases an enormous amount of energy, some of which is thought to be transferred to particles in the surrounding space. These particles are then accelerated to high speeds, becoming cosmic rays. However, while supernovae can account for many cosmic rays, they struggle to explain the most extreme particles seen in the cosmic ray spectrum. As we continue up the spectrum, we reach an even more puzzling feature called the ankle. This marks another dramatic change in the energy of cosmic rays. Above the ankle, cosmic rays become even more energetic, reaching levels that challenge our understanding of particle acceleration. At this point, they are classified as ultra-high-energy cosmic rays, aka UHCRs, and likely originate from extragalactic sources far beyond the Milky Way. These particles are so powerful that they could be accelerated by phenomena associated with supermassive black holes, active galactic nuclei, or even gamma-ray bursts. To put them into perspective, the most energetic cosmic rays detected have energies millions of times greater than the particles accelerated in the Large Hadron Collider. This is equivalent to the energy of a tennis ball traveling at over 100 kilometers per hour, concentrated into a single subatomic particle. Harnessing dangerous particles. Can we turn threats into tools? Rather than being sources of destruction or hazards to avoid, what if we could harness the incredible energies or unique properties of cosmic rays, gamma rays, or even antimatter to benefit our future technologies? The possibility of tapping into these forces is not entirely outside the realm of science fiction. In fact, throughout history, many once dangerous forces, fire, electricity, and nuclear energy, have been successfully harnessed for human benefit. Could the same one day be true for these particles? Antimatter particles carry the potential for enormous energy release through the process of annihilation, which results in the complete conversion of mass into energy, making it far more efficient than traditional chemical or even nuclear reactions. If we could figure out a way to safely produce, store, and control antimatter, it could revolutionize fields like space travel, offering a nearly limitless source of energy for propelling spacecraft. Some scientists even believe that antimatter could power the next generation of spacecraft, allowing humans to reach the farthest corners of the solar system or even interstellar space. However, antimatter is incredibly rare in nature, and producing it in significant quantities requires large amounts of energy. Current particle accelerators, like those at CERN, can produce tiny amounts of antimatter, but at enormous costs and with considerable safety risks. Storing antimatter is another major hurdle, as any contact with ordinary matter would cause an explosive release of energy. Specialized magnetic traps, known as penning traps, are one potential solution for containing antimatter, but they are currently limited to very small quantities. Despite these challenges, researchers continue to explore the potential of antimatter as a future energy source, inspired by its unparalleled efficiency and the vast amount of energy it could unleash. While gamma rays can be lethal in high doses, their energy could also be used in medical applications or even for advanced imaging technologies. Such lasers could have applications in everything from medical treatment to materials science, offering new ways to manipulate matter on an atomic scale. However, generating and controlling gamma rays safely presents significant technical challenges, particularly because of the harmful radiation they emit. Some scientists believe that neutrinos could be used for communication across vast distances in space, as they can travel through almost any material without being blocked or absorbed. Neutrino-based communication could allow spacecraft to send signals through planets or stars without interference, offering a new way to explore the far reaches of space. While much of this research is still speculative, the idea of harnessing dangerous particles for human benefit is not without precedent. In the early 20th century, nuclear energy was considered a purely theoretical and highly dangerous field of study. However, by the mid-20th century, similarly, advances in particle physics, materials science, and engineering could one day allow us to control and utilize the particles that currently pose the greatest threats to human life and infrastructure. Of course, there are significant safety concerns associated with the idea of harnessing dangerous particles. Any technology that involves high-energy particles, antimatter, or gamma rays would need to be carefully regulated to prevent accidents or misuse. The potential for weaponization is also a major concern, as these particles could be used to create incredibly powerful and destructive weapons. And so, today's journey comes to an end. Were there particles that you thought I missed? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.